Hey, good afternoon, everybody. Today has provided us with a lot of fascinating insights, actually, about resource estimation, and it's really opened up a conversation that I think a lot of us have wanted to have. And some of the presentations have actually fed quite nicely into what I'm going to be talking about, which is basically something that we all know is a good thing. Let's work across disciplines, talk to each other, communicate more, and really see how we can add value across the mine value chain. And to do this, I'm going to be discussing a case study in how fairly recently I was able to use an integrated approach to integrate some very high quality geology logging alongside estimation, mine planning, and some environmental geochemistry in order to create a better model. So what are silos? I think we all probably know what I mean. Not these, but having said that, they do actually offer a really good analogy for what I'm talking about here, because they're large, it's a tall structure, it's got no windows, it's used for one purpose. I think any of us in our industry, and indeed any industry actually, can recognize how this happens. And really it doesn't, by working within our own disciplines without communicating across disciplines, it can really prevent problems from being recognised, solutions being found until it's too late, and not being able to share information and potential duplication of work as well. So it's really inefficient. Where tasks are broken down into some sort of production line, it doesn't encourage the creativity that we need to be able to solve problems. And while production lines, were recognised by Henry Ford as being productive in car manufacturing, that's not what we do. So in terms of the mining industry, these are just a small subset, really, of what we're talking about. But we probably all have examples of the data and geology side of things on a site, the youngest, most inexperienced geologist logging thousands of meters of core. Certainly I know I did it myself, and I didn't have much knowledge about where it ended up or how it got used. So there's plenty of examples out there where data, geology, really gets consigned into just this silo without being able to be used as a foundation downstream. As my colleague Neris mentioned earlier on, and indeed many presentations have mentioned this, the idea of integrating geology into the geological model and integrating the geological model into the resource model is really critical for the success, and is really the difference between success and failure often. How often has a resource geologist handed over a resource model to a mine engineer and go, well, that's my work done here, without communicating the risk or confidence or indeed the assumptions made that might really change the path that the mining engineer goes down. And, there's other elements, obviously, metallurgy, geotechnical, environmental and social. And so we end up with, just this generic cartoon, but it talks back as well and speaks to what Mark mentioned earlier, this idea of no accountability or people blaming each other. There's too many options to go, well, that's not really part of what I do, so maybe somebody else will do this. Instead, I like this little kind of cartoon, which, every expertise, every discipline has its place. We're all talking to each other, but we all fit into a bigger picture as well. And so the case study that I'm going to present is about a gold deposit in southeastern Africa. It was at pre-feasibility stage, and indeed my company, CSA Global, had completed the geological model and resource estimate and handed over the model to the mining engineers. And several months later, the client came back and said, as part of our preliminary work, we've done a small number of samples for waste characterization work. And we found that there's some acid forming potential identified, and to mitigate the acid mine drainage, we'd like the mine planners to be able to schedule the movement of material better. And in order to do that, can we get this information somehow into the model? So I suppose the vision that we set out initially was we only had a small number of samples, and of course that's often the case. We make a lot of assumptions and extrapolate on the basis of small numbers of samples, but this was some preliminary work at least, and would allow them to move forward and get a better handle on where they needed to go. What we did have was a really robust database of geological logging. And so we figured out that maybe we'd be able to identify some minerals or some alteration, some veining that would allow us to derive a relationship between what we were seeing in the geochemical results and what was happening in the geology. So the idea was essentially the geochemical results summarized or concluded that certain samples were potentially acid forming, that's PAF, not acid forming, NAF, and acid consuming. So we reviewed the geochemical analysis against the logging. Unfortunately, only 63 out of 88 samples had lithology logging. So it would have been nice at the very beginning, at the design part of this process, if somebody who is familiar with the geological logging or the lack of logging, for example, in historical RC data, had run it, this program had been run by them to ensure that everything had lithology. Out of this 63 samples that had lithology logging, 4 had uncertain geochemical analyses with inconclusive AFP results. So it ended up with just 59 samples that were available for geochemistry and geology investigation. Now, in terms of the relogging program, the reason why there was a very robust geological program there was this project had a lot of historical, several generations of logging. And what had happened when the client had taken over the project, their most experienced chief geologist had come in with many years' experience in similar deposit styles, and had decided to just go through the entire logging and do a relogging program. He used rock boards, he used consistent logging codes, examples of key attributes. It was actually a really good program in terms of upskilling junior geologists on site too. So the sorts of things a lot of us, I'm sure, have seen across sites around the world. So the rock board, the core library. And, just in terms of legends and consistent coding, it all just helped to kind of have a set of locked down codes that, would allow you to actually see something in the data. So in terms of the geochemical results that had come back from the waste characterization work, above the base of complete oxidation, or the BOCO, there were 26 samples that were not acid forming. So as you would expect, 1 was potentially acid forming. Below the BOCO, and that was transitional and fresh material in this case, there were 11 potentially acid-forming samples, 12 that were not acid-forming, and 9 that were acid-consuming. So the conclusion was drawn that there was confidence in the oxidation surface, so the all oxide could be considered not acid-forming. And then there was a set of fields that in discussions with the chief geologist, we were able to identify as being particularly useful for identifying what might be PAF or NAF or acid consuming. And these were the logged minerals, alteration, vein 1, the sulfide, and even the sulfide percentage actually. So we ended up coming up with a hit list of minerals that were appearing in this deposit that were either potentially acid forming, not acid forming, or acid consuming. And they're your sulfides. There's no surprises here really. Oxide minerals for NAF, and then your carbonates from veining for the acid consuming. There was toing and froing as well in this process, because what we were able to integrate was the knowledge from the geologist who had logged this material, where he said, something like pyrrhotite, for example, might be considered a potentially acid forming or indicative of potentially acid forming, but in the presence of pyrite and magnetite, it's actually more likely to be not acid forming, and there's reasons behind that in terms of the geology model. But this just was an iterative process. So the algorithm was really simple. It was a simple count of the instances of PAF, NAF, and acid consuming incidents. where if carbonate veining or alteration was encountered in any one of these key fields, it was counted as an acid-consuming incident. If there were PAF minerals, it was a PAF incident, and if there were NAF minerals, it was a NAF incident. And as I say, all oxide material above Baco was defined as NAF. Potentially acid forming took priority over acid consuming if there were equal instances where the logged sulfide percentage was high, and in our case it was greater than 10%. Sometimes sulfide percentage it's a really difficult one to judge. It's deposit by deposit. It's going to be reliable or not very reliable. We had the advantage of a single person having logged this deposit, so it was quite useful. And so what we were able to do then was test the algorithm on the 59 samples and see, okay, if we did not know what type of material this was, would the algorithm predict what it was? And it resulted in the correct assignment of 10 out of 12 PAF samples, 37 out of 38 NAF, and 6 out of 9 acid consuming. So in the cases of the PAF and NAF where there was, in fact, in all cases, it was because there was no incident actually logged of any of those materials in it. Having said that, for the acid consuming, something interesting came out because two of the 3 incorrectly designated samples actually aligned with some carbonate veining, a northwest-southeast trend that had been mapped on surface and had a subvertical dip. And, it just kind of resulted in being potentially able to integrate some other geological knowledge into this as well. So in terms of the methodology, the lithology file was desurveyed, and they were flagged with mineralization and oxide wireframes. Mineralization was, of course, excluded. It was a waste characterization exercise, and the oxide set to NAF. There were greater than 114,000 samples that were assigned an acid-forming potential code based on the algorithm. There were about 36,000 that weren't assigned a code at all, since they had no logging or no incident of the relevant minerals. And indicators were assigned 1 or 0 based on the codes. Inverse distance weighting squared was used, which resulted in quite a good visual validation. Given that it was an estimation of indicators, not something I'd normally do for an estimate for grade. Dynamic anisotropy was used for potentially acid forming and not acid forming based on dip and dip directions of the sedimentary cycles that had been modelled. Again, going back to the acid consuming material, the surface mapping mapped carbonate veining was used to inform a search ellipse for the acid consuming. And then finally, the acid forming potential of a block was defined based on the majority estimate. So each block had an estimate for PAF, NAF, and acid consuming, and the majority was what was assigned. And here's just a visual of what it ended up looking like, just a cross-section through it, with red being PAF, dark blue being NAF, light blue being acid consuming, and black means not estimated. So you can see that there's some black material within the main zone there, and that's mineralization, so that was excluded. Also, outside of the optimal pit was not estimated, but essentially within the optimal pit, you have all material estimated, and the same color code is assigned to the drill holes. So in terms of the conclusions, well, we were able to do what we had set out to do, which was, and the really critical point was, being able to define some sort of relationship that would allow us to take a small number of samples, link it to geology and some sound principles, and get that code into the block model so that more planning could be done. And it was generally just a good outcome in terms of collaboration as well. And then the overall conclusions is just, going back to this kind of silo effect. I think it's no good for our industry, working that way. I think increased communication can identify problems and create solutions, add value, communicate and innovate. And it's only when we're really kind of interconnected that we can really see the big picture and that's only going to do us good. So thank you for your attention.